Hello. So basically I was thinking about trying to write out a key for this BC term to review and then possibly making a video afterward, but that felt like a waste of time. I felt like I'd end up wasting at least 45 minutes writing out really nice looking written solutions, and then I still have to come make the video. So having said that, I thought about it and decided to just do the video as my written solutions. So obviously I can make a PDF afterwards, but I will say that this does increase the likelihood that I make a mistake on something because I haven't done the problem already once before after thinking about it as I wrote it out. But I'm going to try to do all these problems. As you might tell by the title, these cover all of the major concepts from the first half of Calculus BC that we covered that are still included on the 2020 truncated AP exam. Having said that, there are two other topics, one related to series and one related to the mean value theorem that I just included because I felt like I wanted something there. So take that for what it is. Those concepts will obviously be on the AP exam as well, but they aren't technically term two terms. So I guess if I wanted to do this right, I could write that in there. But in any event, I'm going to go ahead and start. First question, a population of gophers grows according to the differential equation there. That's a spicy differential equation. It is also known that there are 0 gophers at time t equals 3. Use separation of variables to find an expression for g of t such that g of 3 equals 0. Well, as a heads up, I can say these things because I wrote it. This is going to involve inverse trig integrals. It's also going to involve partial fractions. And I mean, I guess technically, even though it's an AB topic, we did cover it at the very beginning. It's also going to include separation of variables. In fact, because this is a differential equation we want to solve, I'm going to actually kick things off by using separation of variables. And then, of course, we'll run into all the integration techniques. So in looking at this, obviously, I want to get the g's on one side and the t's on the other. So again, I'm just going to move pretty fast, but hopefully you'll be okay with this. I'm going to get 1 over, let's see if I do this right, g squared plus 4 on the left side, dg. And on the right side, I'm going to get, it looks like 20 over t squared minus 4 dt. So again, that's not much of a step. That's a pretty quick step to get through that mess. But having said that, that is our first step. We've separated the variables. Now we go to anti-differentiate, and this is where everything goes wild. So as far as the two techniques here, I'm going to have to use two different colors. The first one I'm going to look at, I'll actually do the one on the left over here. First one we're going to look at is the integral on the left. This resembles, and again, this is just me saying it resembles a little bit an integral expression that we studied, 1 over 1 plus x squared. So that one does not fit substitution, it's just the inverse tangent derivative. It's just the integral of the inverse tangent derivative. So having said that, that's going to lead me to think that this is going to involve some sort of inverse tangent. Now it's not ready for me to just do it right away because of the presence of that 4, but at the same time, at least we're in the right ballpark. So there's my first move. I definitely want to do that. On the right side, what stands out to me is that our denominator factors. So this is really the integral of 20 over t plus 2, t minus 2. And because of that ability to factor the denominator into nice pieces, I'm thinking that's going to be partial fractions. So naturally, each of these things is going to require a little bit of work to make happen. And again, I haven't tested this out yet, but there's my thought process. So again, I'm going to go one at a time. So I'm going to focus first on the integral of 1 over g squared plus 4. So now using the strategies I use, I want to make this look like 1 plus something squared. That's my goal. It's my destination. It's my purpose here. So unfortunately, that 4 stands in the way. We can't just take away 3 of them. It just doesn't work that way. So instead, what I'm going to do is I'm going to factor out a 1/4 from this problem. Obviously, it's not going to change our numerator. All it's going to do is, of course, it's going to make that 4 a 1, because it's kind of like we're factoring. You know what? Yeah, I'll just go with that. I won't. Basically, let me put it this way. It's like we're going to factor out a GCF of 4 from the denominator. When we do that, obviously the plus 4 becomes plus 1, but the g squared becomes g squared over 4 because there was no 4 there before. As well, because there's that 4 down below, I gotta leave it in there. Because there's that 4 down below, we can of course pull out the 1/4. We can then rewrite this expression as 1 over, g over 2 squared plus 1. And the reason that's so helpful is that allows us to do u substitution. We can let u equal g over 2. That means du is 1/2 dg. And that means that 2 du is equal to dg. So bring this all back, we'll get 1/4 the integral of 1 over u squared plus 1. That's huge, that looks just like 1 over 1 plus x squared. dg becomes 2 du. And then from there we can clean this up a little bit. That will become 1/2. We'll get 1/2 the inverse tangent of u. And then we can rewrite that as 1/2 the inverse tangent of our u, which was g over 2. So there is our first antiderivative for the left side. It's obviously a lot of work, I can't deny that, but there is our left side. On the right side, we need to perform partial fractions first. So this whole thing, we are going to assume is equal to some number over the first linear factor plus some other number over the second linear factor. When we do that, if we multiply the whole thing, both sides, by t squared minus 4, I do need to put some parentheses in there. We're going to get 20, oops, I'll leave a little more room. We're going to get 20 equals a times t minus 2 plus b times t plus 2. After this, I want to plug in some values to find a and b. I'm going to plug in -2 first. When I do, I'll get 20 equals -4a plus 0, which means a is going to be -5. And if we plug in t equals 2, we'll get that 20 is equal to 0 plus 4b, which means that b is going to equal +5. Given all that, that means on the right side, our integral expression, which was 20 over t squared minus 4, can be rewritten as 5 over t minus 2, note that I'm changing the order to make the positive first, minus 5 over t plus 2, all dt. Given that information, I need to anti-differentiate, but this one comes out really nice. It's 5 natural log of t minus 2 minus 5 natural log of the absolute value of t plus 2, all plus c, of course. But the only thing I want to do is I want to use log properties just to condense this a little bit, because that's a lot of antiderivative there. So I want to make it a little bit smaller, so I'll use the log properties to say this is 5 natural log of t minus 2 over t plus 2, all plus c. And so there is our second antiderivative. So it's a lot of work to reach that point. We may actually need a second page here. We'll see. Okay, so I'm going to move up here now. So with our antiderivatives in place, we now have 1/2 tangent inverse of g over 2 is equal to 5 natural log of the absolute value of t minus 2 over t plus 2, all plus c. At this point, I'm going to evaluate this at the initial condition, which was the point 3, 0. When I put that in and plug in 0, that's going to be 1/2 the tangent inverse of 0. And then on the right side, it's going to be 5 natural log of the absolute value of 1 over 5 plus c. So given that, and that tangent inverse of 0 is 0, that's going to give us that c is equal to -5 natural log of 1/5. Having said that, though, this is going to take a while to work through, so instead I'm going to do something a little bit clever. It's a little out there, but again, this is my first time getting to do the problem. I'm going to bring up that -1 and write this as 5 natural log of, let's see what we got here, 1/5 to the -1 power. And if you rewrite 1/5 to -1 power, you get 5 ln of 5. Now I did commit a linkage error there. Those are supposed to both be negative, but there we go. So we now have our c value. What that gives us is this equation, and I'm going to be a lazy person. I'm going to bring this down. So we just found that our c value is going to be -5 ln of 5. And at this point, we've got a bunch of work to do to clear this all out. So I want to first multiply everything by 2. So I'll multiply by 2 all the way across. After that, I'm going to tangent both sides, or take the tangent of both sides in order to get that cleaned up. So that way g over 2 is going to equal the tangent, I'm getting close to the thing, tangent of 10 ln of all that stuff, t minus 2 over t plus 2, minus 5 ln of 5, oops, sorry, minus 10 ln of 5, because we distributed that 2 in. And then from here, we just got to solve for g, which means multiplying both sides by 2. So hopefully you'll forgive me from saying g will be equal to 2 tangent of that thing. Now, if you're looking at this problem and going, oh my goodness, I'm never going to understand this, it all is too hard. Yeah, well, I admit that I made the problem a little bit tougher just because I wanted to bring a couple ideas together and keep using that idea. But at the same time, I would hope that neither one of these skills, neither that one nor that one, was that difficult. It was really just a combination. So it might be helpful just to clean up the problem and focus on the two sides of separation of variables, kind of like I did with the pink and the red, rather than focusing on trying to solve everything. But at the same time, it does look like we succeeded. At what cost? The second question we're going to look at is naturally number 2. Number 2 deals with a particular concept, and it actually is focused very tightly on this concept, and that is logistic growth. So something that's actually been in the news quite a bit lately, as we talk about trying to flatten the curve. We're trying to get the number of cases to approach a nice asymptote. We're trying to get it as flat as soon as possible, and all that good stuff. So we're talking logistic growth. So first of all, when we talk about this logistic growth, we're going to use this phrase carrying capacity. That represents the asymptote up there, that horizontal asymptote we're trying to approach. But more importantly, the carrying capacity is basically what the population were to reach moving forward. So there's only so much population that can be sustained in a given situation. So our goal is to figure out what that population is going to hit. Now in our situation here, we're talking about the mass of a baby chick giraffe. And if you haven't seen the show Green Eggs and Ham on Netflix, I truly found it enjoyable. It was actually, I think, the first thing that I watched when we went on to the quarantine stuff. It says it satisfies the logistic growth model given over there. It says the chick giraffe has a mass of 42 kilograms at time t equals 0 days. It asks us what is the carrying capacity. And this is an important question. Kind of everything in logistic growth comes from that carrying capacity question. The way to find the carrying capacity is to set dp dt equal to 0 and then find p that is not equal to 0. So what we're looking for is we're looking for the non-zero population, or in this case mass, that makes the differential equation 0. And the idea is the carrying capacity is this asymptote. That's the population that would be sustained by the amount of resources that we have. So once the growth rate, aka the derivative, is 0, that number, that population that's reached right there, would be the carrying capacity. It would flatten out in a sense. This is us literally asking for what population is the growth rate flat. So in this case, we're trying to figure out sort of what the largest mass is for this particular chick giraffe, but whatever the case. So looking on here, if we want to set dp dt equal to 0, we take a look. We see we have p over 6 times 240 minus 3p. Now we did say that p is not equal to 0, so that means that what we're really looking for here is we're trying to figure out when 240 minus 3p is equal to 0. Solving that really quickly gives us p equals 80. So in other words, the carrying capacity mass is going to be 80 kilograms for this chick giraffe. And if memory serves on the show, they look like they were sort of a combination of ostrich giraffe thing. So this one, by the way, is named Mr. Jenkins, just for the record. For part B, find the maximum growth rate of the chick giraffe's mass. So now there are a couple different ways you could approach this. The maximum growth rate is like saying what's the largest derivative value, or what's the maximum value of the derivative. So one way you could do that is you could take the derivative of the derivative, and you could set that equal to 0. And that would give us a clue and figure out the critical numbers of the derivative and work from there. That is absolutely possible, and we'll do that in just a second. But let me point out that the other way is that that population where it occurs is going to be half of the carrying capacity. So there's also some nice values if you know the properties of logistic growth. So there's a couple different ways to get there. So based on this information, we should know that the answer here, since we did 2a already, is going to be 80 over 2 or 40. So that should be our answer. Well, shoot, that should be the population, or in this case, I keep saying population. That should be the mass at which the growth rate is the largest. We would use that to figure out the other thing. But let's go try it the long way just in case. This isn't necessarily a fact that always stuck with me. So if we want to take the derivative of this expression, it would be helpful to have a good way of looking at this derivative that's a little easier to calculate. So if I multiply that through, that's going to simplify to 40p minus 1/2 p squared. So there is our derivative. We want to take the derivative of this expression. That's going to be equal to 40p prime minus p times p prime. There we go. So of course we said we want this to be equal to 0. So factoring this out, p prime would be multiplied times 40 minus p. And if that's going to be true, then obviously what we're looking at is p equals 40, which matches what we have up there. So basically our mass is 40 kilograms. Now that's not the maximum growth rate. That's saying how heavy Mr. Jenkins, or excuse me, the chickaraf would be when it has the maximum growth rate. So what we need to figure out now is what is the growth rate when p is equal to 40. Because that will actually find the largest value of the growth rate rather than what weight the bird creature is at that time. So given that information, that's going to lead us to p over 6 times 240 minus 3 times p. Now truthfully, it'd be tempting just to stop right there and just go, oh, there it is, and I can believe it, but I'll finish. So if I divide by 2, it's going to be 20 over 3. That's going to be 240 minus 120. That's going to be equal to 20 over 3 times 120, which is going to be 40 times 20, which is going to be 800. So the maximum growth rate is 800. I meant to say include units, and in fact I'm betting that on your paper it will say include units. So just in case, following this information, we're talking about a value of the derivative. That would be kilograms per time unit. And looking at the problem, does it ever say anything about time? Yes. It says days. So these chickarafs grow pretty fast. Oops. So 800 kilograms per day would be when it's growing the fastest. For part C, it asks us to evaluate the limit as t approaches infinity of p of t. And naturally, if you're like me, or like I was when I first started teaching that, you go, oh man, I'm going to have to use partial fractions, we're going to have to solve all this stuff, but you do not have to. When you're asked for a population that grows according to logistic growth, what the limit is of the population, or in this case the mass, that's just equal to k, which we know as the carrying capacity. So this is just asking what's this population, or in this case mass, going to do as we continue forward. Sorry, I'm trying to write while also doing that. Well, we already know that. The carrying capacity we said was 80, so the carrying capacity is equal to that limit, which is 80 kilograms. Which means as time goes forward, barring some sort of outside attack or information, outside intervention, I think is the word I was looking for, this chickaraf's mass will hug really close to 80 kilograms. Next, we're going to look at question 3. Question 3 is the one that has the two non-calculus A-B questions, but they're part B and C. For now, we want to go forward with what we have. So, in looking at this first one, I admit that this looks like it's going to be fairly challenging. We're going to be evaluating an integral from 1 to infinity of 6x e to the negative 3x. So, yeah, there's a little bit going on here. So, oh, and I forgot the dx. So now having said that, before we kick anything else off here, talking about the topics that are included in here, first and foremost, it's the first thing you see, this is going to require us to evaluate an improper integral. The presence of that infinity up there means it's not a true definite integral, which is defined on a finite interval. This is one that's extending on forever, so we're going to have to make a slight adjustment involving limits. The other concept that's here that you probably can't see yet, but you will soon enough, is integration by parts. Like technically this is going to require integration by parts because of the combination of a polynomial and an exponential function. but we'll get there in a second. So first I mentioned the improper integrals. The way we fix that is we rewrite this as the limit of a definite integral from 1 to b, and it'll be the limit as b approaches infinity. Sounds kind of rhymey and poemy, but close enough. So as far as everything else on the inside, yeah, it all stays the same. That didn't change at all. Having said that, though, now that we've established this, we have to be really careful about the way we write out our work. Now that we have a limit there, we can't drop the limit if we're going to keep using equal signs, so we will need to be careful in that way. Having said that, though, I'm going to take a moment, and I'm going to just focus on evaluating the antiderivative of this expression. So as I said earlier, this expression is going to require integration by parts. So I'm going to go off to the side for a second and focus on evaluating 6x e to the negative 3x outside the context of that improper integral. I just want to get that out of the way. So consider it sort of I use the star system as like, I'm going to go make a little aside and go work out this stuff over here. So using LIPET to deal with this product inside the integrand, it says we've got a polynomial and an exponential. That means we're going to let the u side be equal to 6x, and the dv line is going to begin with e to the negative 3x. From here, we'll start in differentiating on the u's. So u's derivative will be 6, derivative 6 will be 0. On the other side, with dv, e to the negative 3x, using u substitution would give us a factor of negative 1/3 in front. So this will be negative 1/3 e to the negative 3x. And then differentiating one more time will give us positive 1/9 e to the negative 3x. Finally, with the tic-tac-toe strategy, we go plus, minus, plus. We diagonalize to tic-tac-toe. And we've got our expression for our antiderivative. It's going to be, it looks like 6x times negative 1/3 e to the negative 3x, and then minus 6 times 1/9 e to the negative 3x. And of course we'll have a plus, so we would have a plus c, but we're going to be doing a improper integral in a second, so no worries. This cleans up, it looks like, to negative 2x e to the negative 3x. And then the next one we've got minus 2/3 e to the negative 3x. And for the sake of simplicity and to clean this up just a little bit, I'm going to factor out some GCFs here. I'm going to pull out a negative 2/3 e to the negative 3x, forgive me. That will now leave me with inside, looks like a 3x and a plus 1. So let me just check that really fast. Yes, there it is. Okay, so we have completed our little soliloquy. We're ready to bring this all back together. So this expression is going to be equal to the limit as b approaches infinity of our antiderivative, which we just established as negative 2/3 e to the negative 3x times 3x plus 1, except we're going to evaluate this from 1 to b, knowing, of course, that b is infinity. So in staring at this, we've got a little bit of work to do to evaluate this, but what I'm going to do is I'm going to go ahead and just rewrite it in a slightly different way first. I want us to look at this, just for the purposes of evaluating, as negative 2 times 3x plus 1 divided by, looks like 3 e to the 3x. So please bear with me as you look at that. Make sure it's accurate. Obviously pause if you need to think a little bit, but there's our expression. I made an error though. As I said, I'm going to make more errors the way this is written. The limit as b goes to infinity, and it's evaluated from 1 to b. So in going to attack this thing, it's going to be a little bit of work to do here. This definitely isn't trivial. I'm not good at writing clean problems anymore. So let's see here. We've got, I'm going to write this negative 6. Oops, I'm going to evaluate it and plug in. It's going to be negative 6b minus 2 divided by 3e to the 3b. And then it will be plus 2 times 3 plus 1, or 4, over 3e to the third. So this is what's left for us to evaluate, this limit as b goes to infinity. Now, as far as evaluating goes, we need to really draw our attention to this guy right here, call it double star. If we want to evaluate that limit, you might notice that the first part goes to negative infinity and the bottom part goes to infinity. That tells us L'Hopital is going to work. So because of that, we have the opportunity to use L'Hopital just on that first part, mind you. So this is going to be the same thing as the limit as b goes to infinity of what will amount to negative 6 over 9e to the 3b, and then plus it looks like 8 over 3e cubed. Now when we go to evaluate this, if we plug in infinity, you can probably already see it. It's negative 6 over infinity plus 8 over 3e cubed. And given that information, I think we have everything that we need. Negative 6 over infinity is 0. That means this expression converges to 8 over 3e cubed. That was an adventure itself too. So again, trying to combine a couple skills together, ended up maybe making that a little bit harder than it was, but I think this is a pretty fair question. It's just a challenging problem, really. So there's our answer though. We found that this integral does converge, and the value it converges to appears to be 8 over 3e cubed. Continuing forward with the work using this function L of x, the next question is one of those not a part of term 2, but I think good question. It asks us to what value does this series for L of n converge to? And cleaning this up a little bit, this is equivalent to 4e to the negative 3n. So we want to figure out the value it converges to. Not just does it converge, but what value does it converge to? So what's the sum of this series? So in looking at this doesn't necessarily jump out at me right away. So I'm going to make some cosmetic changes to the summand, the thing on the inside. This is the same thing as 4e to the negative third to the n. You maybe are figuring out where I'm going as soon as I do that. And if I rewrite this just a little bit differently, this becomes 4 times 1 over e cubed to the n power. That is clearly a geometric series. And in particular, it's not only a geometric series, it's a geometric series that has its common ratio equal to 1 over e cubed, which is clearly less than 1. So in fact, the magnitude of that ratio is less than 1. That means that the series converges, which is great information, but we didn't want to settle for just stating that it converges. We want to find what it actually converges to. Specifically though, remember, this series, being geometric, will converge to, converges to a sub 1 over 1 minus r. So our question now amounts to calculating a sub 1 over 1 minus r. In this particular problem, if we plug in 1 to get that leading term, we get 4e to the negative 3. And then in our denominator, we have 1 minus 1 over e cubed. So if you're a efficiency expert, you'd probably stop right there. That is the correct answer. I just don't feel satisfied, so I'm going to continue. Our numerator is 4 over e to the third. Our denominator, if we find a common denominator, is e cubed minus 1 over e to the third. Now, if you like dividing fractions, a good way to do that is to flip the denominator 1 and multiply. So notice the e cubes divide out, and we're left with our value of 4 over e cubed minus 1. And there is our value. We just used it using the same properties of geometric series that you've been studying in this term. Finally, to end part 3, we have part 3c, which asks us to find the x value guaranteed by the mean value theorem for L of x on the interval from 0 to 3. Again, not an AP topic, or that is definitely an AP topic, not a term 2 calculus BC topic, but a topic that could show up as well. So first of all, to point out, I'm going to just state that since L of x is exponential, L of x is both differentiable and continuous. So this is important, particularly in a free response section, because you're expected to state all necessary conditions, prove or demonstrate that all necessary conditions are met when you're proving something or working through a solution on the AP exam, at least on free response. So L is continuous and differentiable. So that means the mean value theorem applies. So beyond that, recall that the mean value theorem says there exists a value of c in the interval from a to b such that the derivative at c is equal to L of b minus L of a all over b minus a. So we've got to calculate the average rate of change and the derivative and then solve an equation involving both. So to help me with this, I'm going to color code them just so that way once again we've got everything kind of kept clean. Do green and red, two classic ones. I'll start with the average rate of change. So the average rate of change in this case is going to be L of 3 minus L of 0, all divided by 3 minus 0. That's going to be equal to e to the negative 9 minus e to the 0, all over 3. That's going to be equivalent to 1 over e to the 9th minus 1 divided by 3. And you can see I'm just kind of I'm just trying to manipulate this so it looks a little bit nicer because it's kind of messy right now. This will become 1 minus e to the 9th over e to the 9th over 3. And then finally, if we condense that the most, we get 1 minus e to the 9th over 3 e to the 9th. So that is our average rate of change. So that's only half the problem. It did involve quite a bit, but it's only half the problem. From here, we also need to take the derivative of L of x. That is going to be negative 3 e to the negative 3x. It's nice to have one of those work out every once in a while. So in here, if we want to solve this equation, we now want to figure out when the red portion, which conveniently kept the equal sign, thanks for that, is equal to this green portion. So what follows is just kind of algebra. I'm going to multiply both sides first by negative 1/3. Now interestingly enough, when I do that, of course we get e to the negative 3x. On the other side, we have this negative sign, so I'm going to distribute the negative sign, just that, into the numerator. That will give me e to the 9th minus 1 divided by 3e to the 9th. Next, we need to solve for x. So I'm going to natural log both sides. So you can see we're not going to get 7 as our answer here. This is going to be the natural log of this mess. And then last but not least, we need to solve for, oh, I kept that e there, it looks like. Now just have negative 3x. And then finally, we just need to multiply by negative 1/3. So wrapping this up, we're going to get that x is equal to negative 1/3 times the natural log of e to the 9th minus 1 over 3e to the 9th. Now I will say, if you're looking, oh, I made a mistake, didn't I? I forgot to multiply the denominator by 3. I can fix it. Let's fix all of those denominators. That's supposed to be a 9. Got distracted by all the other stuff. It's this thing multiplied times this thing. 9, 9, 9. It's the rare situation where I actually caught a mistake as I was working live. But there it is. So again, I'd say this is more of a cumbersome calculation. It's kind of annoying. It's not necessarily the hardest problem. It's just annoying, but it worked. So brings us to the final extended question here, question 4, which involves a table of values. One of those things that I'm just really pretty sure, I feel pretty confident will show up on the AP exam this year. It just seems like a great opportunity to test a bunch of different techniques in a really nice, clean manner. We actually have 2 tables here. We have, oh, and I could have just combined that into a single table, but best laid plans. Table, ignoring where they are, it says that both functions are twice differentiable and that g is a twice differentiable function. G prime is all we have though for g. So for the first one, it says let h of x equal arc cosine of f of x over 2. And we're supposed to evaluate this difference quotient. Well, I'll point out to you, as you can probably predict, that this is really just equal to h prime of 9. So this problem is going to boil down to us differentiating this arc cosine problem. So let's just start there. Let's go ahead and begin. I'll rewrite this in inverse notation as well. Excuse me. So there is our expression. We want to find the derivative of this function. Before we do that, though, I'm going to rewrite it in a cleaner manner. Oops, I figured I want to write that way. Boom. So there's where we start. Why do I start there? Because that allows me to draw a right triangle to represent the situation. So this is the angle y, whose cosine, otherwise known as adjacent over hypotenuse, is equal to f of x over 2. Using the Pythagorean theorem, I'm not even going to show this, we'll get 2 squared minus f of x squared. So there's everything we have. That's helpful, but it doesn't necessarily solve the problem for us because our job here is to get a derivative. We're just going to need that a little later. So I'm going to differentiate both sides with respect to x. On the left, I'll get negative sine of y times y prime, or dy dx. On the right side, I'll get 1/2 f prime of x. Solving for y prime, I'm going to multiply both sides by negative sine. That's going to be equal, or by 1 over negative sine, excuse me. That's going to be equal to 1/2 f prime of x times 1 over negative sine of y. And then I just don't like that notation. It just looks kind of awkward to me. So I'm going to rewrite this as negative f prime of x over 2 times cosecant of y. So I've just kind of rearranged all the ingredients here. Now that we've got that in place, we can pull this out and take a look at what it gives us. So we've just shown basically that h prime of x is equal to negative f prime of x over 2 times the cosecant of y. Well, since sine of y is equal to the square root thing over the hypotenuse, then that means that we can wrap this up as negative f prime of x over 2 times the square root of 4 minus f of x squared divided by, oh, I did that wrong. It's got to be over 2. Bet I messed this up. So 2 over that, so that way it's the reciprocal. Okay, so having done all this, we now have h prime of x. We want h prime of 9, so we need to evaluate this expression at x equals 9. So what does that leave us with? H prime of 9 is equal to negative f prime of 9. That's equal to negative 4 divided by 2. On the other side we have 2, so the 2's will divide out. In our denominator, we'll have the square root of 4 minus f of 9. F of 9 is root 3, which means that this will be root 3 squared, or 3. Which, are you kidding me after all that? This is going to be equal to 4 over 1 times 1 over the square root of 1, which equals 4. All of that to get an answer of 4. I can't even be mad at anyone. I wrote the question. Just feels like that was a lot to get to 4. But hey, we got our answer, so there it is. Oh, and I'm sorry, I didn't write what concepts. This is pretty well focused on inverse trig derivatives. Obviously, there's some chain rule involved here. There's some other stuff going on. You're reading a table, difference quotient, but the BC concept was the inverse trig derivative, something we did in BC. For part B, now this one's actually going to be a little easier. It won't be as bad. It's probably one of the lighter questions on here. It says to approximate the arc length of g of x. I'm going to underline that for us. The arc length of g of x for x between -1 and 9 using LRAM and 3 subintervals. Well, now in your mind, you might think to yourself, like, how am I going to use LRAM? Like, where is that going to pop up in here? But the truth is, it has to do with what information we're provided. Since all we know about g are 4 values of g prime, we're stuck having to do an approximation. So let's start this way. What is the formula for the arc length? Well, this is something you definitely want to know. It's going to be the integral from -1 to 9 of the square root of 1 plus the derivative squared. When I say derivative, it's the derivative of the function, which in our case is g prime of x. So this is what we need to approximate. And we're going to approximate it using LRAM and 3 subintervals. So setting this thing up, we're basically going to approximate an integrals value, a definite integrals value, except this definite integrals integrand has a square root and a 1 and a g prime squared. So that's what we're going to be approximating. So in order to get here, of course, our L is going to be approximately equal to, since we're doing LRAM and that includes width times height, we can write out our widths first. It'll be 2 minus a negative 1 for the first one. Then we'll leave some space. Then we'll have 4 minus 2. And we'll leave some space. And then we'll have 9 minus 4. So each of those corresponds to a width. The other thing we want to include is we want to include the heights. And the heights are going to be based on the square root of 1 plus g prime of x squared. That's going to be the structure, at least for what we have. So for the first one, we'll have the square root of 1 plus, then we'll have g prime squared. As far as which value we'll be plugging in, since we're using LRAM, we're going to use the left values. So we're going to be using g prime of negative 1. For the next one, we'll have 1 plus, and then we'll use g prime of 2, since that's the left endpoint on the interval from 2 to 4. Finally, we'll have the square root of 1 plus, and then it'll be g prime of the left endpoint, which is 4 in this case. So I'm going to try to clean this up just a little bit because there's a lot going on here and there's a lot written. We can't stop here because we have unevaluated functions, so we'll try to wrap this up. We'll get 3 for the first part. Then we'll have the square root of 1 plus g prime of negative 1 squared. Next, we'll have plus 2, and then we'll deal with the square root. It's going to be 1 plus g prime of 2. It's going to be root 35, or negative root 35 squared, which is just going to be plus 35. And last but not least, we're going to have 5 times the square root of 1 plus g prime of 4, which is right here. By the way, that is the same thing as root 8. So this is going to be 1 plus 8. Doesn't have to be squared because it's really root 8 squared. I should probably just write that. So there is our expression. Technically at this point we're done. We could stop right there with our answer. But if we want to go a little further, we'll have 3 root 5. We'll have 2 plus the square root of 36, which is 2 times 6, or 12. And then we'll have, it looks like 5 times the square root of 1 plus 8, which is 5 times the square root of 9, which is 15. So if we want to clean this up, we get 3 root 5 plus 27. And there is our approximate arc length. So that's about how long the curve would be based on just this little bit of data that we have. And now, of course, if you did RAM by mistake, or if you tried it with RAM, you'd get a different answer because we'd have extra data or different data. But having said that, we've got all that we needed here. The last question I anticipate is going to be by far the hardest. But at the same time, it's the one I'm most excited about. It was the one that inspired this entire activity. So it says let v of x equal 2f double prime plus 6. So what does that look like? I have no idea. It says the region bounded between v of x and y equals 0 for 2 to 4 is revolved about the vertical line x equals negative 3 to form a solid. Find the volume of the solid. So this is going to be a challenge. I'm not going to lie. Definitely didn't intend it that way, but, well, I did. I definitely wanted it to be a challenge. That was my goal. Are you kidding me? Whatever. Okay, so here's what we got. There's my stuff. I want to draw out what this thing actually looks like. Of course I can't because I didn't draw it well enough. There we go. Okay, so in looking at this expression, I want to draw 2f double prime of 6. I don't know what that looks like. I'm just going to draw it like this. I don't know. So there's our region. We're going to revolve it about the line negative 3. And this isn't drawn very well to scale, but that's probably going to be to our advantage. There's our picture. And now here, something I want to point out is since we're revolving about a vertical line and we don't have the information to solve this equation for x, means the only way that we can approach this is with the BC topic of cylinders. So we're going to need to use the cylinder method in order to evaluate this. So I'm going to draw a representative cylinder in here, just to kind of help me see. Shoot. Eyes kind of went really blurry suddenly. I don't know why that was. So there's our cylinder that we're looking at. As we said, this is -3. And then recall that the cylinder expression we get is 2 pi times the integral of r times h. So given all this, we're going to set up our cylinder integral so that we can actually evaluate this. So looking at this expression, we'll get v equals 2 pi. Feel really confident this is going to run from 2 to 4 as well. As far as the inside, our radius going right minus left, there's right minus left. Right minus left is going to be x minus a -3. And then our height is just going to be 2f double prime of x plus 6. So this is going to be a challenge to multiply out, but I guess we've gotten this far. I'm looking at it going, no, I don't really want to do that, but I can do it. I'm ready to do it. So cleaning this up a little bit, just so we've got a little more room to work with, or we've got a little more hope of working through it, this will be rewritten as 2x f double prime of x plus 6x plus 6 f double prime of x plus 18. So there is our integral. So far, so good. We now need to evaluate this. So I'm going to be completely honest with you. Evaluating this does not look like the most fun I've ever had. Having said that, though, 3 of the terms in our integrand are actually really easy to work with. These 3 are actually all just things we can evaluate straight up. They're just perfect anti-differentiation opportunities. The real problem for us is the fact that we have this monstrosity to deal with. So I'm going to actually do another one of those little asides, and I'm going to go off to here, and I'm going to try to just anti-differentiate that one. So ignoring the definite integral part, I'm going to have 2x f double prime of x. So now looking at this, if we want to evaluate it, of course we've got to choose how to evaluate it, but I noticed that there's a product of 2 different expressions, and in fact by recognizing that product you might notice that this has one other BC topic, which is integration by parts, the anti-product rule. Now, there's nothing in LIPET to tell us which one to choose where here, because we don't know what f double prime is, but the one thing that I can see here is that if I put f double prime here, then that would bring us f triple prime to the 4th derivative. That wouldn't help us because we don't have information about further derivatives. We only know about f and f prime. So what I'm going to do is I'm going to make the executive decision to let u be 2x and dv be the 2nd derivative. That allows us to get the 2nd level of u as, or du as 2, and then the 3rd level would be 0. On the other side, the integral, or the antiderivative f double prime, is f prime, and the antiderivative of that is just f of x. So when we add the tic-tac-toes plus minus plus, we draw our arrows. It turns out that this is equal to 2x f prime of x minus 2f of x. And actually, that's really what we needed. Obviously, there's a plus c there, but for the moment, here, I'll do this. For the moment, we accomplished what we wanted. We now know what that expression is going to be over in our integral. So I think it's time for us to actually dig in and evaluate. So again, I'll draw a line here just to separate that. In this space, we'll have 2 pi times. We'll have our antiderivative here, 2x f prime of x minus 2f of x. That's our antiderivative. The antiderivative of 6x is 3x squared. The antiderivative of 6f double prime is 6f prime of x. Then we can actually combine, we can't, dang it. Oh well. And then the antiderivative of 18 is just 18x. And we're going to evaluate this whole thing from 2 to 4. So be prepared for, I was going to say adventure. I'm not sure adventure is the right word. Be prepared for a little bit of intense work. There we go. Okay, so digging in from here, we've got a lot of evaluating to do. So that 2 pi is on the outside. Dealing with the first one, we're going to get 8 f prime of 4. F prime of 4 is 7, so 8 times 7. Then we'll have minus 2 times f of 4. 2 times f of 4. 2 times 5 is 10, but I guess we'll deal with that in a second. Then we'll have 16 times 3 plus 48 plus 6f prime. 6f prime, oh, plus 42. That makes me happy. Plus 72. Then we're going to subtract the other one. Oh, geez. Oh, man, this is going to be one I don't want to simplify. Subtract this whole thing? Okay. Yeah, we'll do that. This other one, we're going to subtract. Still inside the 2 pi thing, it's being multiplied. We'll have 2 times x, or 4 f prime of 2. So f prime of 2 is 3, so 4 times 3. Minus 2 times f prime, or f of 2, which is negative 1. Looks like plus 6 f prime of 2 plus 18 times 2 plus 36. Oh boy, I really just want to circle this thing, but I'm here. Gotten this far. That's 56 minus 10 is 46 plus 48 plus 6 plus 42 plus 72 minus, we'll have 12 plus 2 is 14 plus, I feel like I made a mistake in there. Did I miss a term? 1, 2, 3, 4. Yeah, I did. I missed a term. There needs to be a plus 12 in there also. So we'll have minus. We have 12 plus 2 is 14. 26. 32. Yeah. Do it one more time. 12, 14, 26. Plus 18 is 44. Plus 36 is 50, 80. So minus 80. Oh, I'm so sorry. Shouldn't have added that plus 6. It was all my fault there. 46, that's 94, 100. 142 minus 8, which is 134. Which is 268 pi. Oh, the odds of me getting through that without any issue are fairly small, but I did all that work. So I think I'm just going to stop there and just accept that this turned out a little bit more cumbersome. I still don't think it's like hard, it's just intense. So I totally forgive you if you stopped early on many of these problems even, just to save yourself the trouble. But that is the best effort that I can offer. And again, if you happen to catch any errors in here, please let me know. I feel like there's probably one in there. It's so tempting to get that. In fact, I'm looking at it right now going, no, I guess that looks okay. Trying to see if I caught one, but there it is. So anyway, there is a review in the format of the AP exam, but I seriously doubt that the AP exam will be this difficult to compute the answers for. I think it'll be much cleaner than that. But having said that, thank you for watching. Have a great night.